Hi, everybody. So my name is Dave Mariani. Thanks for that introduction. Just a little bit of background on myself. More than that, that was my LinkedIn profile. It's like, ooh, I got to update that thing. Really, most of my experience in big data really came out of Yahoo. So me and my team were responsible for the data pipelines at Yahoo and for all the analytics users. So at Yahoo, two parts of the business, advertising, which is search and display, and of course, our audience, which is all our web properties. So the business model is to attract users so that we can sell advertising. So it's all really a big data problem. And at Yahoo, we collect 10 petabytes of data every day. And we had to actually make that data available and usable by the business. So, so that was my responsibility. We happened to be there. I happened to be there at a time when Hadoop was being incubated. And the reason why we invented Hadoop was because we were really bankrupting ourselves when it came to collecting and storing the data. And really because we always had the policy of never throwing data away. And so to do that, we needed to really invent a whole new subsystem to be able to archive data and then retrieve it as quickly as possible. So that's where the whole idea for Hadoop actually came from, was really out of necessity. But at the same time, what was really tough was taking that data out of that great shared nothing, open source clustered format, and then making it available to business users. And that was my job. And to do that was like incredibly hard. So I started AtScale because it was a journey. I wrote a white paper back in 2010 about how we needed to solve this problem. And here we are in 2015 with a company that I hope is doing that. So today I'm going to spend some time on going through basically what some of the things we uncovered and dealt with at Yahoo. Some of the things you can do with this amazing new platform called Hadoop, especially when it comes to actually putting it into the hands and making it workable for the business. So before I actually start, I just want to get a couple, just to know my audience a little bit better. If you could raise your hand if, do you guys work with Hadoop? Do you work, how many people work with Hadoop? Okay, good. How many people are data scientists? Okay. How many people are on the IT side of the house? Okay. And then how many people are traditional BI users in the business? Okay, it's a good mix. I noticed some of you raised your hand twice, so you're on both sides of the house. Okay, so that's really helpful to know. So let's get started. What I'm going to be doing today is I'm going to get a little bit technical. I'm going to show you some techniques of different ways of modeling data. If we have time, we could do a demo, and I could show you one of the ways we can use that data. But for the most part, let's just keep it. Let's keep it not too high level, but I want to get a little nitty gritty here, so you can get something to take away here. So these are really sort of the do's and don'ts that I've learned over the years when I've run big data operations. So after Yahoo, I also ran a big data operation for Klout, and it was really at Klout where we actually ingested about half of Facebook's data and made it available as a service. But really, you know, the first real sort of don't comes from my Yahoo days, which basically don't throw data away. That seems to be obvious, but what we've been doing over the years with traditional data warehousing is that we've tended to take the data and actually before we actually decide to actually archive it, we actually want to process it and aggregate it and structure it. And when we have to do that and you add that overhead, then actually capturing and storing data and archiving data is actually an expensive operation. So what we learned at Yahoo was don't worry about structuring the data. Just capture it as is, as it comes off of the applications and the log files for those applications. And then worry about applying the structure later. And don't move and copy data. So, from the beginning of business intelligence, we've always had to take data out of its original captured form and load it into a database engine. Put it back into rows and columns. And that's, again, copying the data is no longer really feasible with the amount of data that we're capturing today. At Yahoo, with 10 petabytes of data, we still copied data, and I'll show you where we did it, and it was crazy and made my life really, really hard. The other piece is what we know in traditional BI and in data processing and data warehousing, it's all about trying to scale up on the hardware. When I say scale up, it's to try to buy the biggest box we can to make this thing run. And the beauty of Hadoop is that it is truly a shared nothing cluster. And there's been examples of this that haven't been open source. It's what Teradata is. It's what Netezza is. Those were all proprietary clusters of compute. Well, now you have an open source free cluster of compute that you can put together and get the same kind of capabilities of scaling out your data without having to worry about running out of gas when it comes to the hardware to store and process that data as it grows. I'm going to show you some interesting things about schema on demand. And this is something that people don't talk about yet. And it's so imperative for when you start thinking about data and how you store data in Hadoop. Because one of the reasons why we invented Hadoop was to archive without breaking the bank. But one of the other sort of core principles of Hadoop was that the data that we were generating was very, very different. I mean, every application has its own form. And the natural form of those applications could be JSON. It could be maps and arrays. It could be XML. And those don't really conform to rows and columns very well. So what I see a lot of people doing with Hadoop these days is they sort of carry that star schema, data warehousing kind of methodology. They carry it into the Hadoop landscape. And if you do that, you're losing a whole set of capabilities and the agility that comes along with those capabilities if you kind of repeat that mistake. Finally, it's like it's just keep it open. I'm going to show you that there's a lot of options in the open source community, especially with SQL and Hadoop engines. And what you think of Hive, it's not just Hive anymore. There's actually 5 or 6 flavors of Hive. And so we'll talk a little bit about those flavors and what the advantages are of each. So let's just start with not throwing data away. When I started in this back in the 80s, we were really excited because the data warehouse was supposed to be the thing to solve every problem. Right? We moved data from this mainframe, which was basically a file-based system, which was off and behind some scary walls, and nobody had access to it except for people who could write COBOL or write JCL. And then it came into the relational databases where now I can write SQL queries, and we're like, wow, this is it. We finally can put all this data and make it available to anybody who wants to use it. And what really happened was something actually much worse. We ended up with a bunch of silos. You think about some of our customers are big financial institutions, and literally they have 100 BI tools. One of the big banks has 100 business intelligence tools. One of everything. And guess what? Each of those BI tools have their own proprietary data source behind it. So when you think about, Eric was talking about, Blue Talon was talking about security, and oh my God, to somebody who runs IT, who has to manage this data, it's crazy. Because now you have business users and departments creating their own sense of reality, applying their own security, or probably not at all, and all that data is out there costing a lot of money because it's been copied 1 million times, and it's in 1 million different formats, impossible to share. So the difference is that, the data lake thing is so overused, but it is something that's important to understand. The data lake. What does a data lake mean? What a data lake means is that it's a place where you just go park data. It doesn't mean it's a place where you structure data and put it into rows and columns. It's literally an archive. It's a place you throw data. And again, that whole concept of applying structure to the data just when you need it is paramount. And I'll show you some of the techniques to do that, because you probably don't believe it's even possible. Because you're like, yeah, right, how am I going to be able to query data that's in JSON format that's sitting in the data lake? But that's the whole reason why Hadoop was, the second reason why Hadoop was born, was not just for scale, but for flexibility. And the system of serities and the system of understanding natively complex data types is what really changes the game for us all. So moving data. So let's talk about moving data for a second. I don't think we even realize how much we do this. But here's a traditional sort of data warehousing stack. I had multiples of these at Yahoo and at Klout. The data warehouse at the very bottom there was actually, at Yahoo, we were the first ones to use Hadoop as a data warehouse. So that, at least that's good. You know, we're starting someplace not with a big expensive relational database model or a Teradata or a Netezza that cost us $100,000 a terabyte. At least we're doing a little bit better there. But then all the hell breaks loose, and we do the same thing that everybody else does. For my audience data marts, I wrote literally hundreds of pig scripts, not me personally, but my team, to basically extract data and land it into Oracle RAC data marts, all backed by big expensive EMC SANs or NetApp appliances. And then what we do is we plug in, on the audience side, we plug in MicroStrategy as a query engine, and then we plug in MicroStrategy for the UI. On the advertising side, similar stacked, except that we had analysis services, SQL Server analysis services as a query engine, and then we had Tableau and custom applications in Excel as the query tools, the analysis tools. So what did I just do there? I wrote data actually 3 times in this case. So my 10 petabytes of data, I wrote it 3 times. First to Hadoop, then to Oracle, and then I loaded it into the query engine so it could be consumed. So by doing that, of course, I didn't copy 10 petabytes 3 times, because you know what? Each time you move up that curve, you get the fall off. You're able to process less and less. So at the very end, you end up seeing the tip of the iceberg, because you've only been able to afford to expose the data that you deem to be worthy for the business for that moment. And of course, you know that changes. So because that changes, we end up redoing this model in this picture over and over again.
But did you gain performance?
Well, that's why people do it, right? People do it for performance. So I mean, I'll tell you, like so Hadoop was a batch environment and was not queryable at the time. That's why we had to write ETL, because we had to put it into rows and columns in Oracle. So we needed that star schema. And the star schema then supported that query engine, because now the data was queryable. So yeah, it was all because not just performance, but also accessibility. Because the BI tools couldn't understand the data that's landed in Hadoop. So I had to do that. And so what I'm going to tell you here today is that I'll tell you today is that this is what we can achieve now. Is that what we have to understand is we have to get rid of that whole prejudice, the way of thinking that says that we have to put data into a queryable form. Now, 5 years ago, this wasn't possible, but really with the advance of Hive becoming an interactive query environment, this is now possible at scale. So the tools like Impala and Spark SQL, Hive Tez to a lesser degree, all make it possible to move those query workloads directly down into the Hadoop layer. That lets you take advantage and take out all those gray layers that we just passed up. So if I can write data once, and then I can apply a schema on that data at query time, as closest to the user as possible, I have all new possibilities in terms of how I combine data and how I look at the grain of data. I can go as low as I want because I haven't pre-aggregated it or thrown things away as I traveled up that stack. What's the other don't? Don't lock yourself in. So here is, as a vendor selling proprietary software, I'm going to say don't buy proprietary software unless you really, really have to. And what's interesting is about the Hadoop stack is that there's just a ton of value there and a ton of innovation. So you don't want to fight that curve. Now for the enterprise, what we find is that with anything like open source, it's always an 80-20. Open source will usually take you 80% of the way there, and then you got to fill in the 20%. At Yahoo, I had 200 people to fill in the 20%. But at an enterprise whose business is to do something else other than data, you don't really have that luxury. But I can tell you can go a long way with that 80% with what's free and available to you today. So here's an example, and I pulled this example straight off of, this is off of SAP's site. And the engineer wrote it because the engineer was sort of tooting his own horn about how great and how fast Hana was. Now, SAP Hana is super expensive. I mean, I heard some people say it's $1 million a terabyte, and I wouldn't doubt it, right? But here's something interesting. They compared it to Impala. So what is Impala? Impala is a SQL on Hadoop engine. It's a Hive-compatible MPP database for Hadoop. And I want you to look at those two columns. This is a TPCH data set. I think it's TPCH, TPCH. And what you can see there is that the engineer was comparing the performance of Hana in EC2. And if you look at these queries here, and you look at the sample set, and you look at that when it comes to Hana, look, Hana is doing pretty well. And actually, this is a filtered set. And there's some cases where Hana actually beat Impala. But guess what? Hana cost $1 million, and Impala's for free. And guess what? It's the hardware that Impala goes on, meaning the Hadoop cluster, is commodity. It's not a custom hardware software solution. So I looked at this and I said, wow, you just sold me on why I should never buy a proprietary MPP architecture. So the Teradatas and the Netezas and the Hanas, it's like when you think about that and you think about where I'm going to park my data, it's time to start thinking differently there. Because your options are so much better. And I'm not saying that Impala is better than Hana. Look, I'm sure there's use cases it's always going to be better. And when it comes to price for the money, you're talking about orders of magnitude cheaper. And it's not just Impala. So Hive, at Yahoo, I had a hard time using Hive because Hive was actually invented at Facebook. And at Yahoo, we invented Hadoop, and so our founders were very prejudiced against any kind of advancement that came outside of Yahoo. But you know what? Hive was great. Why was Hive great? Because it got me out of the business of writing stupid MapReduce code. And it got me to be able to use a query interface, a standard query interface, to actually access what is essentially raw files on that Hadoop cluster. Because that's all Hadoop is, by the way. It's just a file system, and you know that. Literally just files. We went from mainframe, which was files, to relational, which was binary, back to files on Hadoop. It's like we come full circle now. But what the problem with Hive, and the problem we had with Hive, is that the fastest query I could run on Hive, on a one-row table, was 45 seconds. So that's not interactive. That's not how Oracle behaves. Oracle would return, that query in tens of milliseconds, if even that. So what was really missing was interactive query on Hadoop, and that's where these different SQL and Hadoop engines come in. And you can look at sort of the different sort of matrices of the pros and cons. Impala probably has had the most time out there. Impala is sponsored by Cloudera. It's the most like an MPP architecture, but on Hadoop. Spark SQL is basically a SQL interface into Spark, and that's come up and that's gotten better, but not nearly as I think as good as Impala at this point, but it's close. Hive Tez is from Hortonworks, and it's really just Hive. and Tez is the interactive portion of Hive. So Hive Tez is the purest thing. It really truly is Hive. And then you have Drill and Presto. Drill and Presto Drill is by MapR. It's more of an MPP style. Presto is also kind of an MPP style. It's also sponsored by Facebook. And they all have different sort of pros and cons. But you could see that there's new ones that are being added all the time. I think LinkedIn just announced Pentaho, which is their own version of this, not too long ago. So all these engines, what they have in common is the Hive Metastore. So the Hive Metastore is really become the common semantic layer for files on Hadoop. And that's really important, because it means that if you can use Hive to describe your crazy files, and you can, Hive's very rich, it can handle all that complexity of JSON and XML and maps and arrays, then you can put what looks like a table interface on your file system in Hadoop, and you can make that compatible with all the tools that understand SQL. So that's why these things are so darn important. So what to do? Scale out, not up. I'm going to give you an example of what I did at Yahoo. So this is a slide straight out of a presentation we did at a couple conferences explaining what we did. So the Tau was our platform for display advertising optimization. The Tau platform generated $50 million of lift every year in Yahoo's advertising business. So this was essentially a cube. It was a SQL Server analysis cube. So it was all based on the biggest SQL box I could buy, which was 25 cores and 128 gigs at the time, which was crazy expensive. But I want to show you what happened here. So the Tau cube, which was 24 terabytes, was the largest cube on Earth, still is, by a factor of 5. The next closest was Microsoft's own Ad Center cube, which was 5 terabytes. So what's so crazy is that look at what the data was that we were capturing that I wanted to process. 2 petabytes a day in my Hadoop cluster, and I wanted it all. And guess what? I had to boil it down into 24 terabytes, which is by far the largest cube on the planet, but completely inadequate in terms of what I actually wanted to do. And why? It was inadequate because that little box right there, it was an example of scale up. I can't cluster that. I can't cluster cubing technology. So since I can't cluster it, that means I have to just buy the biggest box and be really smart about how I load it. That's not a scalable architecture. When people talk about OLAP, and I talk about OLAP, and they're like, oh, that's so 80s. And it is. The physical OLAP is, you think about what happened to OLAP is that every business user loves OLAP. They don't know what it means, but when they see measures and dimensions and hierarchies and crosstabs, it's completely natural. And yet this technology completely stopped. It was unable to meet the demands of our data growth and our data complexity. So what happened was that we just threw out OLAP, and it just became for finance. And then we had to make everybody learn SQL. So all the BI tools out there now speak SQL, which is really kind of sad. When I combined OLAP with Tableau, that's what generated $50 million worth of lift. Was because now my business users, my ad optimizers could go ahead and find ways of tuning ad campaigns in flight and add that much value just by using OLAP on a 24 terabyte cube. So what's the difference now with Hadoop? I pulled this straight off of Cloudera's site, and it's just it's a study. You can go see this. About whether the SQL and Hadoop engines are horizontally scalable. So let me explain the slide. So in red, you have the time of queries. This is against a bunch of benchmarks. These are identical clusters. The red bars are for 18 nodes, and the blue bars are for 36 nodes. So the point is to show this is these bars should be pretty much the same. because on the 36 nodes, we doubled the data. So we went from 15 terabytes to 30 terabytes. And so what you see there is that on these TPC DS benchmarks, that you can see that it scales out pretty horizontally. So that means that I can double my number of nodes and double my performance. I can double my data, and if I double my nodes, I have the same performance. So as a guy who is managing the data pipelines and the data warehousing, if I could solve my problem by adding more nodes to my cluster as the data grows, woohoo! You know, that's it, right? That's the nirvana. I don't have to re-engineer my applications or go and buy some scary proprietary technology that does something magical under the hood and has all these side effects and costs that go along with it. So let me show you another example. So this is for a customer who says, look, I need to have my queries return in 4 seconds or less. And the first line here is, and what you're seeing here is the number of dimensions on the horizontal scale. So this is for, the blue line is for SQL Server Analysis Services. This is a very large credit card company, where everybody knows. You probably have it in your pocket. And what they have is this is an application to do fraud and credit risk. So the point here is that they're looking at data in a cube, they're finding the patterns of fraud, and they're drilling down to the lowest they can go before they actually do an investigation. And the problem was with MOLAP type technology like SQL Server Analysis Services is that you start to get this crazy scale where when you add more and more dimensions to the data, your queries will slow down in an order of magnitude, almost logarithmic scale. Here's an example of what it looks like with Spark SQL. So with Spark SQL, what you see is, first of all, it's like, it's like you definitely have a difference in speed almost along the whole path. Spark SQL is slower than analysis services, except when you get into the large number of dimensions. So this is an example of, look, Hadoop and Hadoop scale out is really helping us here. With SQL Server Analysis Services and scale up, we're starting to hit our limits. So the key here is, and this is what we did, is that what we were able to do is through the use of aggregations on the Hadoop cluster, is that we're able to achieve the better or the same performance as a MOLAP model where you pre-calculate everything with a combination of Spark SQL and aggregations. So you can see that I can get, with the right sort of combination of technology with Hadoop, I can have my cake and eat it too. I can have OLAP again, so my business users get speed and they get that ease of use without having to write SQL. And as an IT guy, I get my scale out because I can add more nodes as my data grows. Okay, so now schema on demand. So we'll get a real life example here. Well, so first of all, this is one of my customers' star schema. This is coming out of analysis services, and that's pretty scary. I mean, and what makes it really scary is that we have to do this for our BI tools today. We have to do this craziness. Because the BI tools want a star schema. They want fact tables and they want dimension tables. Even though that whole model of dimensions exist inside the data now. Dimensions are in the facts. Yet we still have to build these stupid dimension tables in order to make the BI tools work. And that's just unsustainable. So this is why everybody, is why data warehousing projects fail almost a large majority of the time. It's hard to see, sorry, but it doesn't matter. Just look at the complexity of how I go from a new piece of data to making it visible in someone's dashboard. I got to go through all these steps. And each of these steps have different loops back to each other. And each of these steps have different people involved, whether they be DBAs or BI guys or storage guys. The SAN and the NAS guys. You got the DBAs and you got crazy amount of people here. It takes an army to actually get your data queryable. But this is how you can do it instead. So this is how you can remove all those layers. So I'm going to take you through an example here, and this is an example of a gaming customer. So I remember at lunch, I met a gentleman who works for a gaming company. And this happens to be a gaming customer. And what they want to do is, you know, you think about when you're writing an online game, you're writing a multiplayer game, you have two things that you're interested in. The game designers are interested in making the game more fun to play, so you drive engagement and you drive usage. The money guys, the guys that you make money by selling most of the time virtual goods. So you have to analyze what people are doing so you can optimize on both of those vectors. So what we did is we came up with the world's most simplest data model. And that's what you see on top. So let's break it down. I have two rows here. I have one log file, and one log file, there's tab delimited columns in it. So what you see down in the middle here on the mapping is that's a Hive external table DDL statement. So what I'm doing here is I'm creating a Hive table. It's not a loaded table. It's just really a skeleton. It's a skeleton that's going to point back to the file on HDFS, which is just a tab delimited file. So the first thing I did is, as I said, the first column is going to be the event. And that's important because I can now generate, this gaming company, the designers can instrument a new event, and that ends up just turning it into a new row in the log file. So that's great. Now I have every event. If I want to add a new event, I can, and it instantly shows up in my data. And of course, there are certain things that are always the same. What time did the event happen? What user generated the event? But then look at this. Every event is different, and every event has different properties associated with it, right? And so what we would do is that if you did this relationally, if I had 10 events and each had 10 properties, I would have 100 columns. And only 10, and what you would look at is it would be hugely sparse because it would be most of the columns, 90 of the columns would not be filled in for each event, right? It's this complete waste of space. And when I want to go add a new event or a new event attribute, now I have to add more columns, and that's almost impossible. So in this model, instead, all our event attributes are just maps, meaning key values. So you can see there's a location, there's an item, there's a referral, there's an amount. That was a purchased good. You can see there's a login event, again, location, the rank of the user, the client that the user was logging in on. So now I can add or take away events and event attributes anytime I want, and it's automatically going to show up into my data. So then how do I query that then? Well, what I do is when I create that Hive table, I create it as a map data type. You can see that there's a string, there's a timestamp, there's an integer, but then there's a map of a string comma string. Now what that means is that if you see in the query down below, what I'm now doing is I'm materializing the location and the rank dimension literally at query time. So that is what's meant by query on read. Because now what I've done is I've applied that structure at the last possible moment. So now I can write stream data to my Hadoop cluster. As a new event appears, I can instantly view that event as soon as it shows up. That's powerful stuff. So let's look at I'll get into a demo. So I'm going to show you, this is a game called, let's see if this shows up. Let's see if it shows up. Come on, you can play. Okay, this is what the user says. I'll have to explain it. So Dota is called Defense. It's a multiplayer game, very popular. Lots of guys on my office play it. It's Defense Against the Ancients is what it stood for. It's one of the most popular multiplayer games in the world. And what it is that there's 5 players on 2 teams, and they play each other in a match. And in those matches, they pick a hero, which is an avatar, and then those heroes have different powers or items that they use, and they earn gold. So that's the nature of this game. Now what's cool, and the reason why I'm using this game, it's by Valve, is that they make all the data available online for you. So if you wanted to go test this yourself, you can go to their website and you can actually subscribe to the data in real time and stream it and collect it. And the way that data looks is it looks like this. Sorry for the small type. But there's three basic, there's actually one data structure. The first data structure is called match details. And what you're seeing there is you're seeing that you can see there's a players, and you can see players is actually a struct. And you see that on the right in player details. So here in player details, you can see there's a whole payload of additional attributes about that player. And in the player, you can see there's also a Steam user at the very bottom. That's also a struct. So on the right, you can see now the Steam user, you can see the player profile. So what they've done is that they've compiled in basically one row per game. So even though there's 10 players, and all those 10 players have all different attributes and different things that they've done, they've taken a single match and made it into one single row. So when you think about what you'd have to do in a relational land, think of all the table joining you would have to do. And what Hadoop hates is Hadoop hates joining. So because Hadoop hates it because it's a shared nothing environment. It wants to scan all data and process it on its own. Once it has to join, now you're sending data across nodes and you're shuffling data, and then that's when its horizontal scale goes off the cliff. So this is how you want to process data. It's already all together. Now, what you would do if you weren't familiar with what Hadoop could do is what you would do is you probably go and split this all out into a million different tables, and then at query time you join it again, and you'd be so sorry because the data would be so latent, expensive, and slow. Instead, what I do is I take that data and I literally, in HDFS, I do a make directory for games, and then I just put the file that I collected from the Dota website straight into, it's a JSON file, that's just JSON, straight into HDFS. So by doing the HDFS put, I've copied the data, that single data file into my Hadoop cluster. If I have a 10-node cluster, that data file has now been broken up in 10 different ways. So now when I read it back, it goes 10 times faster because it's 10 times smaller because I split it up across and spread it across all these different disk drives. So then what I did is I said, okay, well, let's create a Hive table so I can query this sucker. So this is how we did it. Again, it's an external table. External means don't load it, just point to the file that's on disk. So there's no latency there. And then you can see that there's all the different, you can see that there's the player. You can see the player is an array of structures. Because remember, there's 10 players. So now I'm going to have 10 people in that array, and then I have a player structure. And I also have this ability upgrade stuff, and then there's my Steam user. So for each user in that array, I also have their profile attributes as a struct. So now how do I query this sucker? So who are the most popular heroes in the game? So here's the important construct. Right in the middle there, you can see that lateral view explode players. What I basically have done is in that one statement, I've treated the player's embedded structure as another embedded table. So what I've done is I've taken that and I've materialized it at runtime. So now there's no more joins. I can still get to all that player, all that embedded data, and query it, but now I'm querying one table and I'm querying it in true parallel fashion. Because I'm not shuffling data around, I'm reading it all in parallel on those different Hadoop nodes. That's powerful. Here's a more advanced version of this. Which heroes have the highest win rate? Well, you can see there, what I did is, again, I exploded the players, and then I have another nested data structure where I've taken the player's team and figured out which team they were on to determine what the win was. And there's two teams, Dire and Radiant. And that's why you see that there. And that's the syntax for accessing it. You can see it's player.team. Here's even a more complicated case. What are the top 3 items associated with the best win rate? Again, it's like, it's all right there for you. And yeah, this is getting a little hairy now, but the reason, and there's better ways of doing this, but what I'm trying to tell you and show you is that literally I can answer any question without really having to move or transform the data and put it into another form. So as it lands, it's there for me and it's there for me to query. So that's really the key here, is that joins are really the enemy of business, BI, and processing altogether. And if I can leverage the Hadoop model, the Hive model, and take advantage of its core capabilities, I can eliminate joins wherever possible. And if I can do that, I can do great things like time series analysis. So just for session data, if any of you had to deal with web logs, and like having to sessionize is terrible, right? Well, imagine if I could have a whole session in one row, where each page was an array of pages in that session. That makes it pretty easy. Affinity analysis, segment analysis, many-to-many. Many-to-many, think about many-to-many for a second. Well, I just gave you an example with the pages there. It's like many-to-many doesn't have to be joining two different tables anymore to do a Cartesian product. Now many-to-many can be just an explosion of an array inside that row. It's there and it comes for free. So there are, I'm out of time, so I'm not going to give you a demo. I'd love to give you a demo of the AtScale platform later, but I just wanted to talk to you a little bit about to make that work for BI tools. Hadoop has traditionally not been very friendly to BI tools. And with this whole data lake that we've been talking about, the value of that data lake and the value of being able to materialize that and put that in the hands of a business user is enormous. And that's really our business. The problem is that connecting those BI tools as they are straight to that data lake, it's just too slow and it's not at all user-friendly. You saw those SQL statements, right? That's kind of scary. So what we've done is we basically created this semantic layer, a virtual cube. So just like you saw a virtual table in Hive, we've created virtual cubes for Hadoop that connect the business user to the data lake. And it gives both sides what they need. It gives IT the kind of control they want, because they're control freaks. I am a control freak. And it gives the business the kind of flexibility and freedom to self-serve on the data. So that's it. It's if you just kind of follow these basic tenets, you can really change how you and your company deal with data, and you can stop dropping data on the floor and actually use it to run the business.